So, in this last section, we will talk about the cell unbalance. And this is a very common challenge that affects the battery packs over time. Here we will discuss this problem, but also we will find the different methods and balancing methods that are used to prevent and to correct the imbalance in our battery packs. So let's start by defining what is the cell unbalance. Ideally, all of the cells on a battery pack should have the same state of charge, and this is needed to ensure an uniform performance in our battery. For example, in a completely new battery pack, the cells are going to be closely matched by the manufacturer, trying to make them reach their charge and discharge limits simultaneously. In other words, that will mean also that all of the cells in the battery pack will operate with the same voltage, and it will ensure that the energy is going to be efficiently distributed in all of the cells, and also that that will prevent and will extend, it will prevent aging and will extend the lifespan of our battery. However, due to the battery aging, also due to manufacturing tolerances in our cells, and also to the variation in the cells temperatures that each of these cells may experience during their life, or even because of different self-discharge rates in the batteries, the reality is that the cells will start to imbalance, and difference between the state of charge will start to emerge. So in an imbalanced battery pack, some of the cells may drift apart from the charge level of the others, and as a result, the battery pack performance becomes limited by the weakest cell, which reaches the voltage limits first. This will force the entire pack, for instance, to stop charging or to stop discharging prematurely, and not to use all the capacity that the battery has, but only a portion of it. This is one example where we can see that in this case we have a pack that is composed of 5 different cells, and we are starting with all of the cells being discharged. As long as we start charging, we see that some of these cells are imbalanced. As you can see, the cell number 4 has a state of charge significantly lower than the cell number 5 that has the maximum state of charge. As we continue charging, at some point one of the cells will reach the overvoltage in the battery sooner than the others. In this case, the charging has to be interrupted because charge number 5 is completely charged, and we need to prevent the overcharging in order to avoid a safety risk in the battery. So at the end of charging, as you can see, only cell number 5 has a 100% state of charge. Cell number 1 and 2 are almost charged, but cell number 3 and 4 are significantly disbalanced. What causes is that there is a lot of energy that we are not using of our cells. If we guarantee that they are all being charged at the same time, they are gonna be all charged until the 100% SOC, and then once we use that energy, we will have it available. In this case, we are losing all of this capacity because of not having the cells being balanced. So summarizing this, some of the effects of having the cells in balance is, the first one is that we will have reduced usable capacity, since in this case the weakest cells will dictate the pack limits, and the energy that could have been utilized from healthier cells will at the end get unused. Also, this will increase the stress in some of the cells. So overcharging or deep discharging specific cells can accelerate their aging and reduce the overall lifespan. As you can see here, for instance, if we continue cycling this battery without performing any balancing, cell number 5 will always experience a higher voltage, and accordingly it will also degrade faster than the other cells that will not be fully charged. Cell imbalance can also have thermal instability, and this is going to be a safety risk since will increase the overheating and possible failure because of that. In order to prevent all of these issues, the battery management system must to incorporate the balancing techniques, and these are techniques that will look to equalize the charge levels across all of the cells. These methods will finally ensure that not single cell is overworked and improve the overall efficiency and the safety on the battery pack. And in the next section, we will discuss some of the causes of the cell imbalance and how this can be addressed by the cell balancing. So, before seeing how to actually correct the problem, let's see what are the causes of the problem. So in the battery packs, the cell imbalance is caused by anything that will make one of the cells' state of charge diverge from the others, and this difference can arise due to several factors that are going to be related to the manufacturing, to the operating conditions, or to the battery aging that is normal in our cells. Nonetheless, we can classify the cells imbalance in three main types of imbalance. The first one that we have here is the capacity imbalance. Each battery cell that composes our battery pack can have slightly different capacities due to the manufacturing tolerances. Even though cells are designed to be identical, small variations in the materials and in the process that are being used will result in differences in the capacity, and over time those differences become more and more pronounced, leading to variations in the state of charge levels after we perform each of the charge and discharge cycles. In this case, the cells that have the lower capacity will reach, for instance, the voltage limits faster, and the cells that have the lower capacity are going to be the ones that will be limiting the pack performance because they will cause the pack to shut down earlier than expected. The other type of imbalance is the SOC imbalance, that is also commonly referred to the self-discharge. This is a phenomenon, it's a natural phenomenon in our battery cells, where basically the cells will lose energy even when they are not in use, and this can be related to a leakage of energy that the cell have. So in our battery pack, some of the cells may discharge faster than the others due to variations in the internal chemical processes and also in the reactions that are happening in the battery and so on. So as a result, the cells with the higher self-discharge rate will gradually drift apart from the rest, and this will lead also to imbalances on our battery over time. And the last one is the impedance mismatch. So as has been mentioned before, each battery pack has an internal resistance or an internal impedance, which may affect the efficiency of the battery. Variations in the cell's impedance will lead to voltage differences in our battery pack when they are being loaded. It means when we have the current flowing through the battery. In this case, the battery that have and the battery cells that have the higher impedances will generate more heat, and also it will experience larger voltage drops, making them discharge faster compared to the other battery cells that have a smaller internal resistance. All of these factors, whether they are caused by production variations, self-discharge, or impedance differences, all of those will contribute to the cell imbalance, and if they are left unattended, and if we don't perform any corrective, if we don't use any correction into that, it can cause potential safety risk and also shorten significantly the battery lifespan and be a problem also for the efficiency of our system. To combat these challenges, then we have the cell balancing techniques that will be explored in the next slides. And here let's start explaining what the cell balancing is then. This is going to be a crucial function in the battery management system, and it will basically ensure that all of the cells in our battery pack have an equal state of charge level. The goal here is to prevent any cell from becoming overcharged or over-discharged sooner than the others by equalizing and correcting all the imbalances that we explored before. The balancing methods that we are going to be using and that we are going to be explaining are very important because of several reasons. The one is that it will help us to maximize the usable capacity, to prolong the battery lifetime, and to enhance the safety as well as to improve the general performance. This is again graphically to see what happens with or why do we need the cell balancing. So here we start with a battery that is again composed by 5 cells, and at the beginning all of the cells will deliver the same energy, and all of the cells will have the same state of charge, since they are completely identical and they are coming already matched from the manufacturer. As we start cycling them, and this example, after 100 cycles, we see that there are already some difference between the state of charge, and for instance cell number 3 and cell number 4 already deviate in the state of charge to the other two. This will cause, as was mentioned, for instance, the sooner shutdown in charging or during discharging, and also it will cause it will prevent us to utilize the full energy potential of our battery. To correct this, then we perform the cell balancing, and throughout balancing what we are going to do is to make all of the cells to share the same state of charge and to equalize them again to make them be as close as possible as to its initial state. And this is going to be something that is executed in every cycle. So in this example, we left unattended our battery during 100 cycles, and because of that the deviation was very big. But after each cycle we have to already balance and correct this phenomenon. In general, there are 2 primary types of cell balancing methods. We have passive balancing or we have active balancing. In the passive balancing, basically it will work dissipating the excess of energy from the higher charged cells, and this allows the lower charged cells to catch up. This is typically achieved using resistors that are going to be connected in parallel to each individual cells. So let's see how does the passive balancing works. In this case, we have the 5 cells, and we are going to highlight the cells that has the maximum state of charge and the cells that have the minimum state of charge. When any of the cells reaches a predefined threshold, the BMS will monitor the voltage of all of the cells and will activate the balancing resistance to drain the excess of charge. In this case, for instance, all of the cells that have a state of charge higher than the one with the minimum state of charge, that is this one, those will need to drain the excess of charge. So as you can see here, cells 1, 2, even cell number 3 a little bit, and cell number 5 will start draining that energy until the point that they all have the same state of charge. Some of the advantages of this method is that it's very simple and it is cost effective to implement, and also it requires not so many components. However, the biggest problem that we have with this method is that the energy that we have in these cells that is causing the differences, all that excess of energy is gonna be waste, and it will be only producing heat. It will not be used for anything. And at the end, this will reduce the overall efficiency of our system. Additionally, with this method, we will take longer times to equalize all of the cells compared, for instance, with the active method. And it is not ideal with applications that will require a lot of energy efficiency, because, as mentioned, we are burning the excess of energy and we are using the cell with the lowest state of charge as the reference to waste the energy of all of the cells that have a higher state of charge than this one. On the other side, then, there is the active balancing. And in the active balancing, what we will do is to redistribute the excess of energy from those cells that have a higher state of charge to the ones that have a lower state of charge. In this case, rather than dissipating it as heat, the excess of energy, we won't be dissipating it, but we will be transferring from one cell to another. And in order to do that, we will be using some components, electronic components that are capable of storing energy, such as, for instance, the capacitors, inductors, or transformer. And that's going to be the agent that help us to collect energy from one of the cells and then to transfer it to another one. So how does this method works? So in the active balancing, as was mentioned, the energy is going to be temporarily stored in an intermediate component that is going to be the capacitor, the inductor of the transformer, and then it's going to be transferred to the cells with the lower charge. This will dynamically transfer energy from within all of our battery pack and to reach to the point where we will have the optimal energy distribution. So in this example over here, we are starting with the same condition when one of the cells is having the maximum state of charge and another one is the minimum state of charge. Here, instead of using the one of minimum state of charge as the reference and trying to make all of the other cells to reach the lowest SOC, what we are going to do is to start sharing energy between all of the cells, discharging using the energy of the cells that have more energy to charge those ones that have less energy. And as you can see, at the end, it will be more efficient since all of our cells will have a higher state of charge. Because of this, one of the biggest advantages of active balancing is that it has higher energy utilization, as it is being distributed rather than waste. It also prolongs the battery lifetime because it reduces the stress of the batteries, and it is ideal for high performance applications, for instance in electric vehicles and energy storage systems. The problem with this is that it is way more complex and it is more costly to implement because it requires additional circuitry and also additional components that need to be included here, and all of that will make more expensive and more hard to implement this solution. Now, this is like the two main strategies, but inside or we can detail exactly what are the methods that are used in each of these strategies, and that is what we are going to discuss next, starting with the one of the passive balancing techniques, that is the fixed shunt resistor method. So, as we explained, in the passive balancing, what we are trying to do at the end is to bring the cells to the same state of charge by dissipating the excess of energy. In this specific method, we are using fixed resistors that are going to be permanently connected in parallel to each of the cells of our battery pack. As we can see here, each of these represent our battery cells, and we have a permanent connection to the battery, to the balancing resistors. When we reach the balancing condition, the excess of energy will be dissipated through these resistors as heat, and will allow the cells that have the higher voltages to burn that energy. The idea here is that based on Ohm's law, the higher voltage cells will experience greater balancing current because the current will be equal to the voltage divided by the resistance, and this will cause them to self-discharge more rapidly than those that have lower voltages. The problem, and it is very important to mention that here, is that in this system we will be continuously dissipating and continuously wasting energy, even with the battery is not being used. So this is a big problem for our system because it is not very inefficient. Also, when do we use this? We use it in very small battery packs, very small applications that are cost sensitive, when we are trying to minimize at much the number of components that we are using in our BMS, and when we don't have option to include, for instance, active control on the balancing resistance that we are having here. But it is not recommended, and I personally wouldn't use it in any applications. This permanent self-discharge can even put our battery in an unsafe conditions when we drain the cells too much. The next balancing method is then this switched balancing resistor. This balancing will provide a way much better control of the balancing process compared to the previous ones. In this case, in the switch shunt resistor method, the resistors are not going to be permanently connected to the battery cells, but instead we will use a switch that is typically controlled by our BMS, and this switch will connect and disconnect the resistors only from those cells that need to waste the energy. In this case, the balancing process will work in three main steps. In the first step, the BMS will be continuously monitoring the voltage that will correlate with the state of charge of the batteries in the packs. And in the second step, when any of our cells will exceed the predefined or the voltage difference that is allowed as threshold to activate the balancing, and when the balancing conditions are met, the BMS will start activating the switches of those cells that need to drain energy. And this, when we turn on those switches, we allow the excess of energy to be dissipated through these resistors. Once the balancing has been completed, all of the switches are going to be open, and this will prevent further energy losses, and also it will prevent to have the battery to be continuously self-discharged. We can calculate that what is the power that is being dissipated in these resistors, and basically they are going to be equal to the voltage of our cells multiplied by the current that is flowing through the resistor. Some of the advantages of this in comparison to the previous is that only the energy is going to be dissipated when needed, and this minimizes unnecessary losses in our system. Also, the BMS, as it dynamically adjusts the balancing based on the operating conditions and cell requirements, it is smarter, and it optimizes the waste of the energy, so reduces as well the generation of heat, and it's in overall beneficial for our battery packs. The problems is that, or disadvantages is that it requires more complex control circuits, and also it includes more components, so it has higher cost. But if still, if we compare it with active balancing, this passive switch resistor balancing, it's cheaper, and on the other side, it will take longer time to equalize the battery cells. Now let's move to the active balancing techniques, and we will start with these multiple switch capacitors methods. In this case, unlike in the passive balancing, which dissipates the excess of energy as heat, in the active balancing, as was explained, we will try to redistribute the energy from those cells that have more energy to those that have less energy, eliminating the waste of energy. So in this approach, as you can see, we have an array of capacitors and also an array of switches that are used to transfer the energy between cells inside of our battery pack. So the capacitors are components that will act as temporary storage devices to move the energy from one cell to another. The process in this case will start with identifying what are those cells that have the higher capacity, or the higher energy, and the capacitor is then connected to those high voltage cells through the switches that we can see here, and this allows us to charge this capacitor up to the cells voltage that we have. Then the switch will disconnect and the capacitor is reconnected to one of the cells that have the lower cell voltage. When we connect it to that cell, then the capacitor will be discharged, and in that way it will deliver the energy to the target cell. This cycle will be repeated across the entire battery pack until all of the battery cells are being balanced. In general, unlike passive methods, this technique is way more efficient, and it reduces the thermal stress of the components and of our batteries, so improving also the reliability of these systems. It is also suitable for medium-sized battery pack applications because it's modular and it can be relatively simple, easily implemented. In the disadvantages is that, as you can see, it requires a lot of switches and also capacitors that increase the cost and increase the complexity of the system. It is more expensive compared to the passive balancing, and also it requires more complex control strategies. And finally, in this particular case, the balancing process occurs in very discrete steps. It means that it might take longer compared to other active methods, especially because in this particular case we are going to be limited to transferring energy only in adjacent cells. So it means that, for instance, if I want this is the cell that has the maximum energy, and this one is the cell that has the minimum energy, the cells are going to start sharing between adjacent cells until the enough energy is transferred to this one that is far away. But this takes a lot of steps, transferring from one cell to the next one, and from that one to the next one, and so on until it reaches the target cell. Another method is then the one-switched capacitor, and this technique uses a single capacitor to transfer the energy between the cells, and this makes it way more cost-effective approach than the previous one, where we had several capacitors and several switches. In this case, the balancing process will work with 3 steps. In the first step, what we're going to do is with this network or switches, we will connect this capacitor to the cell that has the higher voltage, and like this, the single capacitor will be charged. Then the switch will disconnect and the capacitor will reconnect to that cell that has the lower cell voltage, and like this it will that cell will be charged and the capacitor will be discharged to transfer the energy. And this process is repeated across the whole battery pack again, moving from one cell to another the energy. The amount of cell that can be transferred by the capacitor will depend on the capacitance of the element, as well as the difference in the voltage between the maximum cell and the minimum cell voltage in our battery pack. The advantages that this method has is that compared to the multiple switch capacitor method, it will require fewer components, and that makes it more simple, and also most cheaper. It reduces the waste of energy in comparison to the passive methods, and it is lightweight. It works very well with small systems. However, it is very slow during the balancing, because we only have one component that is working doing the transfer of energy from one cell to another, and this is bad especially in large battery pack, where we need also to be able to balance our battery fast. It also will require complex control strategies for managing the switching process of all of these components, and to ensure that the energy is being transferred between the right cells. And the final and more advanced and efficient balancing that we have is the switched transformer that you can see over here. This is a complex method that will allow us for rapid and efficient energy transfer across multiple cells, and this makes it ideal in large battery packs that will require the quick and reliable balancing that maybe neither the passive nor the capacitive balancing techniques allows us to have. So in this method, we will use a transformer that you can see over here, and this transformer will be the component that will be transferring the energy again from this and distributing the energy along all of our battery cells. This is going to be achieved by rapidly switching the primary coil that you can see over here, and this will generate an AC waveform that we can relate to the secondary coils and send that energy to the target cells. I will try to explain this a little bit better, because it's more complex than the previous balancing methods. So as you can see here, the primary side of this transformer, that it is over here, it is going to be connected across a group of cells. All of these cells are going to be connected to this primary coil of our transformer. And if you see over here, there is also a switching device. And this switching device will be activated and deactivated very fast, in such a way that we will create an alternative current waveform that allows us to transfer the energy to this through the transformer. Then this alternating current waveform, this AC waveform, will generate a magnetic field in the core of our transformer, and this will induce then a proportional voltage in the secondary winding. The voltage that is gonna be produced in the secondary winding will depend on the turns ratio of our transformer that we can see over here. The secondary voltage is then gonna be directed to the cell that has the lowest voltage, or the cells that needs to be charged and where we need to redistribute the energy. So using the switches over here, the BMS will dynamically connect the transformer to the different cells as it is needed, ensuring that the cells are going to be balanced effectively over time. This requires sophisticated algorithms that will control when and where the balancing occurs, and will also optimize, for instance, the control of this AC waveform, and will also control in which cells to inject the energy that is going to be transferred. Some of the advantages of this method is that it has minimal losses, so it is very efficient. Also, it is a method that I think is the fastest, so it quickly balances even very large battery packs that has many battery cells that are connected in series. This method also reduces the stress of individual cells and will extend the lifespan of the battery, and at the end it is very used in complex applications and very high power applications. The disadvantages of this relies in the complexity, and the implementation of the switched transformer requires advanced control circuitry as well as some power electronics background for making it work correctly. Also, the transformer and the control circuit will increase the overall cost of the BMS, and also I guess it will take more space and more weight of our system to put that transformer there. With this, we have concluded with all of the balancing methods. Depending on the application and the requirements, again, we can use which method to use. The passive balancing method that have switched resistance is widely used even in energy storage systems because it's very cost effective, whether, for instance, these transformer solutions are very efficient for electric vehicles and can be implemented in more demanding applications.